Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey Houston, projectile motion type 3. There's 4 types. We're almost there. In this case, we're going to be launching a projectile, but the height that it lands will be different than the height that it started. So a classic example, this would be a baseball player. The baseball player hits the ball, but he hits it at a height, and it goes here, and then it lands on the ground with a different height, right? He hits it at a meter, and it falls some further distance. So that's the classic part of this type 3 problem, where now that we have a different height. So let's put some numbers in there. So we got a baseball player. He's launching a baseball at a height of 1.21 meters. And his angle of trajectory is 38 degrees. And he hits it at 40, that's pretty fast, 44.7 meters per second. All right, we want to ask 3 questions. Time. What is his total time in the air? Hang time, if you will. Number 2 is displacement. What does that mean? How far did it travel? So how far did the ball go? Did it go how far? And what is his final velocity? Now the last problem, the final velocity equaled the initial velocity, but this is not going to be true here because it's going to be going faster because of the acceleration of gravity is further down. So let's take a look at how we can do this. Again, x and y. What do we know? Let's do distance, dx. That's what we're trying to find right here, displacement. Placement. dy, we don't know that either. We might be able to calculate that. So, all right. vix and viy, we know these, or we'll figure this out with cosines and sines. We've also got, actually we do know this, the dix initially, what do we know that? That is 1.21 meters. And then, of course, time, we don't know that yet. But these are going to solve this. So let's solve for vix and viy. This would be the sines and the cosine business, right? So let's just put that over here, right? So if it's at, what was the angle again? 38 degrees. So if I do vix, right? So this is at 38 degrees, and this is at 44.7, and this is the adjacent, and this is the opposite. So the x, vix, is going to be equal to cos of 38 equals vix over 44.7 vix. You can do the math. I won't belabor this. This is 35.2. And for VIY, we'll do the sine, the same ball game, and we get 27.5. So we have those numbers, okay? And we also know, by the way, the acceleration. I should know that. Acceleration is 9.8 because we're on the Earth. If we're somewhere else, it'll be somewhere else. Okay, so now we want to figure out some things. All right, so let's do time. Time is the easiest one. So, what's the equation? So this is one that's a little tricky. All right, so let's do time first. Because time, notice how we like to solve for time first because it solves everything. Okay, so we can say delta dy is equal to viy times t plus 1/2 gt squared. Now, this is an important thing. We do know what delta dy is. Actually, let's think about this. Actually, this delta dy, this is going to be negative 1.2 meters. We do know that, right? So this is negative 1.2 meters is equal to the VIY 27.5 times t plus, I'll just say, negative 4.9, that's 1/2 g, times t squared. Now we do have a quadratic function, don't we? So if I have to reset this up, I'll say 0 equals 4.9 t squared plus 27.5 t plus 1.2. I plug this into my quadratic formula. I won't go belabor this. And you get t here to be equal to 5.66 seconds. All right? If you need help on how to use the quadratic formula, I'll help you. So that's the time. So the question, time. 5.6 seconds. Got that? Okay. Question number 2 says, what's the total displacement? How far has it traveled? This is super easy. So because we know the VIX and we know the total distance time that he traveled, right, which is this 5.6 seconds, I know he's traveling 35.2. So part 2, if you will, we can say velocity is distance over time. I want to find distance. The velocity is 35. This is in the x direction, right? Because that's the far he goes. 35.2 is equal to d over 5.66. You rearrange, you solve for d, and d comes out to be 199 meters. So he's going to hit this ball 199 meters. That's far, by the way. That's like 600 feet. I don't know that you can do that. That would be like the best baseball player in the world. Okay, and what's the final velocity? Now this one is the trickiest one. Well, let's do that. So let's look at the third question. In this question we want to say, what is VIY at the end, right? So this is VIY, and that's the hard question, right? Because we've got, he's falling, he was going up at 27.5. So what, we know his vertical speed, or horizontal speed, is 35.2. And at this point, when it's even, it's 35.2. So what we need to do is figure out kind of how much faster he's going. Now, kind of a shortcut is we can use this equation, if you recall. We can say VIY squared, find these from the equation sheet, right, equals, or V final y squared, this should be final, equals V initial squared, this would be y, plus 2a delta dy. Again, from the equation sheet. Now, I know the initial speed in the y direction, right? And that is going to be 27.5. So this is 27.5 squared plus 2 times 9.8. And what we've got going on here is the distance he's going to travel is 1.21 meters, right? And then when we plug that into the equation, we get this whole ball game adds up to 781. All right, and that equals V final squared. We take the square root of both of them, and you get, and we take the square root of this, you get V final to be 27.9 meters per second. You might notice here, this was 27.5, this is 27.9. It only fell an additional 1.21 meters, so it's not a huge significant thing. But the question wasn't what's the, this is V final in the y directions, it's asking what's the V final total. So this is just a simple problem where this is 27.9 in the y direction, and then the x direction didn't change. This was 35.2. We do Pythagorean theorem, 35.2 squared plus 27.9 squared equals, and take the square root of it, and you do all the math, and you get V2 to be 44.9 meters per second. Take the square root. And so that's the answer. You could also determine what that angle is by taking and doing some sines and cosines if need be. And lastly in this, let's do the extension. So now we have a little different situation in this particular thing. We want to see if the pitcher can catch the ball. So if he hits it in a line drive towards the pitcher, can the pitcher catch the ball? Can he put his arm, if you will, and catch the ball? So the issue is we know that the pitcher is 18.44 meters away from the batter. He has a vertical reach of 1.71 meters. Can he catch the ball? So what we're going to do is, again, time is the variable. We want to know how much time the ball is in the air at 18.4 meters. So remember that we know our VIX. So we're going to plug that into the VIX. So, you know, velocity, and do the x, is equal to distance the x divided by time. And the velocity we knew is 35.2. So I say 35.2 is equal to, we want to find the at 18.4, 18.44 divided by time, rearrange, we solve for time, we get t to be equal to 0.52 seconds. So within a half a second, can he get his ham up to 1.71 meters? So now we're going to plug this in the y equation, right? Delta dy is equal to VIY times t, or delta t, plus 1/2 AT squared, 1/2 AT squared. So VIY, let's go back to that, that's the 27.5, so equals 27.5 times our time, 0.52 seconds, plus, and I'll say negative 4.9, g if you will is negative, times 0.52 squared. Do the math, and what you get for delta dy to be equal to dy is 13.1 meters. This man has no hope. 13.1 meters. This catcher has no hope of catching this, because if this ball is 13 meters, he has reached 1.71. There's not even a prayer he's going to hit. He's going to catch this ball. Not ever. Not any. No one can jump that high. So yeah, no, not going to happen. It's an impossible jump. No one can jump that high. So again, do you see how time kind of makes our connection between the x's and the y's? We use the x, then we plugged in the y, we solved the problem. Hey Houston, we don't have a problem because projectile motion, it ain't so hard because you guys are rock stars. You're good. We'll see you in class.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.